Hello everyone. So we have been following this particular flow for understanding design compiler, understanding the synthesis flow. So in the last lecture we saw how to define the design environment. Before that we saw how to write the RTL and how to use that RTL in design compiler, assuming the libraries are all in place. Last lecture we focused on the setting of design environment, which includes setting of the operating conditions, of input loading conditions, output loading conditions, and so on. So now that our design is ready, our operating conditions and environment conditions are defined. Now we need to set our performance goals. So this group of goals is called collectively called design constraints. So just try and understand the difference between the design environment and design constraints. For example, let's say a chip has n number of designs which will get synthesized separately. Now each of those designs will probably have the exact same design environment. Why? Because each of these blocks is expected to work at the similar range of PVTs since all these blocks belong to the same chip. They will probably most likely they will have, although the input and output loading conditions might differ for each block, but operating conditions, wire load model, etc. would be same for all those blocks. But each of them will have a custom set of design constraints. When we look at the design constraints in detail, we will see what are these and why will they be different from block to block. Okay, so we will focus on the two sets of commands here: design rule constraints and design optimization constraints. And again, so this lecture would be the end of setting up the block for synthesis. In the next one, we will look at the different compile strategies and the actual compile command. So now design constraints are majorly of two types. First is the design rule constraints. Design rule constraints are, in most of the cases, they are implicit constraints, and they come from the standard cell library, the logic library, or whatever cells we are using might not be standard cells, might be an analog macro, a memory, a PLL, for example. So each of the cell, each of the macro, whether it be a standard cell or an analog macro, will define these implicit constraints for itself. These constraints are, it is must to meet these constraints to make sure that design functions correctly. So any design that uses a library will inherit these constraints, and by default they have a higher priority over other optimization constraints. The second group is the optimization constraints themselves. These are explicit constraints, that means they need to be defined by the user. They represent the design goals, that is the performance or speed, power and area. So during optimization, DC will try and meet these constraints, meet these goals, but it will make sure that design rule constraints are met first. The higher priority is given to design rule constraints. But let's say you specify some area figure to DC, it might not meet area at the cost of violating the design rule constraint. It will never try and meet timing by violating the design rule constraint. So first and foremost, design rule constraint should be met, then comes the performance thing. Obviously, when we say since the optimization constraints represent the target area, power and speed, they should be realistic enough for DC to work on them. This is the graphical representation of the kind of a flow chart representing what are the different type of constraints. So design rule constraints, The most important of them is the maximum, that is maximum transition time, maximum fan out, maximum capacitance. We will not look at cell degradation. Cell degradation is not exactly used by design compiler. It is used by some other features of design compiler, like I guess this is used by design compiler topographical. There's a command tool called DC topo, but that is outside the scope of our of the course. There's a minimum capacitance command also. It is very rarely used. So we'll focus on the maximum for this lecture. Again, optimization constraints are of two types here: area and speed. We are not talking about power here. I'll have some discussion on power, but for let's say for the sake of this lecture, let's forget about power for now. Let's focus on area and speed. So these are the commands that represent each of the constraint types: set max transition, set max fan out, set max capacitance. For area, set max area. For speed, it's create clock, set input delay, set output delay, or set max delay and delay. Let's look at design rule constraints first. So design rule constraints are technology specific restrictions that the design must meet to ensure functionality. We saw if we go back and to the libraries session and try to remember the nonlinear delay model, we saw that nonlinear delay model is represented by a lookup table. That lookup table, for example, for a buffer or inverter delay from input to output, the delay and the transition at the output will depend on the input transition and the output load. And these lookup tables, the upper limit of so the lookup table will have two indexes, the input transition and the output load. Each of these indexes will have a maximum value associated with it. That means the designer has put a maximum limit for the transition input transition and the output capacitance, and he has run spice on till that maximum point. If the capacitance and transition go beyond those points, then the delay calculation is not deemed to be accurate, because it is then extrapolation is happening. The design compiler will go and will try and calculate the delay, but it will result into extrapolation, and consequently some error will creep in. This is why we say that the design rules have to be met to ensure the functionality of the design. If the design rules are not met, the timing calculation that the tool does is not reliable. So what happens? What does design rule constraints? What do? They will constrain the nets of a design, but the commands run only pins. So let's say you have a max capacitance limit on the output of a cell. So what does that mean is that the capacitance, so the output capacitance seen by the gate will have three factors, will have three components. In fact, one is the inherent gate cap itself, the inherent cap of the output. Other is the cap represented by the net it drives. In the synthesis case, it will mostly be a Weber model. And third is the fan out, that is how many gate it drives, and the capacitance of all those inputs. So the constraint is on the net, but it is associated with the pins of the cell from the logic library. Most of the logic libraries have default design rules. You can open up the Synopsys 1900 library, go to a particular cell. In fact, I showed in one of the library lecture that what is the capacitance of what is the max cap attribute. So each of the output pin of each gate will have a max cap attribute. If the max cap attribute is not there, then the tool will take the default max cap attribute from the header. So typical design rules constrain transition time, fan out loads, and gaps. The additional design rules can also be specified. DC will not violate these, even if it means violating the delay and area goals. We can in fact apply more restrictive constraints that is more restrictive than the limits in the library. But less restrictive constraints cannot be applied. What it means is that the constraints cannot violate the limits. Sorry, the design cannot violate the limits that are coming from the logic library. We could, for some reason, apply a more restrictive limit, but we cannot relax that limit. So we look at the constraint types: maximum condition, maximum fan-out, maximum capacitance. Minimum capacitance is very similar to max cap. It's just the minimum limit. Max cap is the maximum limit. So I will not discuss that separately. So let's look at maximum transition time. So maximum transition time for a net is the longest time required for its driving pin to change logic values. So since the transition time at the input of a gate will determine the delay calculation from input to output, there is a maximum limit on it, and that comes from the library. DC will attempt to make the transition time of each net less than the max trans value. For example, by buffering the output of the driving gate. Max transition. Many times the designers apply max transition limits based on clock frequency, so that can also be done. Transition times are calculated from the non-linear delay model of the library. Please note, synthesis does not have accurate information of nets, and that is why it uses wire load model, for example. So to change, so in most of the cases, you would not need to apply this amount set max transition, because the max trans limits are implicitly coming from the library itself. But if you want to change those values, make them more restrictive, then you could use a set max transition command. If both the library max trans and the set max trans attributes are defined, for example, the library has some value and you apply one more value, more restrictive value using set max function, DC will try to meet the most restrictive value, which sounds logical. So when you start doing synthesis, I would recommend not to use the set max function command. This is used for very specific cases where you know that you want very good transition on some part of the circuit, some part of the design. Only in that case it is used. Second is maximum fan out. So maximum fan out again is a design constraint. Most logic libraries have fan out restrictions on driving pins, creating an implicit fan out constraint. So usually the maximum fan out has two sides. So this constraint is also similar to max trans in the sense that if we apply a more restrictive value using an explicit command, then DC will try to meet the more restrictive one, and obviously the limit cannot be relaxed. So now the fan out has two parts. One is the input part, one is the output part. See this example. Now the driving pin Z sees, so now it drives 4 pins, 2 inverters, 1 output port, and 1 multi-input NOR gate. Now from the library, the value 1.0, that is the fan out load, comes from the library. So this is the fan out load seen at the input of this inverter. So this is in terms of some integers, usually some numbers. Now please note, please go back to the multi-input gate schematic and note that as the number of inputs increase in a gate, the capacitance increases for each gate input. So a multi-input gate will present a greater fan out load compared to a single input gate. So here the inverter, we see inverter has 1, this inverter is also 1, but this multi-input gate has a fan out load of 2. So these values 1, 1 and 2 are coming from the library. You don't have to worry about it. However, on the output port, it is not clear, since this design, this out 1 is the output port of our design, and maybe it is not clear that what kind of load it will drive. So the designer estimated something and set the fan out load to be 3. This is a command set fan out load, which belongs to the category of environment conditions. So the out 1 is supposed to be represent a fan out load of 3. Now the max fan out limit on Z, by virtue of either being defined in the library or using a command of set max fan out, is 8. So it could be either. It could be directly coming from the library, but in this example, the designer specifically sets the set max fan out to be 8 for the pin Z. Now, what DC would do is it will sum up the fan out load presented by the fan out, that is 1 plus 1 plus 2, 4 plus 3, 7, and make sure that the combined fan out load of all the input pins that Z drives is less than the max fan out. So max fan out is given to be 8, the sum is 7, so the constraint is met. Please take some time to understand this example. Note the difference between the fan out load and the max fan out. Fan out load represents the capacitance, the load of the input pin, which are being driven by the relevant output pin. On the other hand, max fan out is an attribute, is a constraint that is defined on the output pin of a cell. Third is the max capacitance. Again, it's a pin level attribute that defines the maximum total capacitance load that the output pin can drive. That is, the pin cannot connect to a net that has a total cap, that is the load cap plus the interconnect cap, greater than or equal to the max cap defined of the pin. Maximum capacitance design rule, it lets us to control the caps of the nets directly. The max cap, the max fan out and max trans will limit the capacitance of the net indirectly. So a long net, for example, will have a bigger cap value, plus it will have a bad transition also. So it will represent both. It will fail both the design rules. It might meet the max fan out because let's say the gate at the end of the long net is a single input gate. So the fan out load won't be much. Again, note that fan out load represents the load presented by the fan out. So let's say there's only one fan out load is less, but the net capacitance itself is pretty bad. It is a big value. So now what will happen is that the output pin of the driving gate will not be able to drive this long wire, and thus it will violate both the max cap and the max trans limit. Max cap will be violated at the output. So max cap is at the output. So please again, I'll take the example of the lookup table. So the inverter delay, for example, depends on the input transition at load, and that is why there is a max trans limit on the input. It depends on the output cap at the output pin. That's why max cap is a constraint defined at the output. So it is very similar in behavior to max trans, but the cost is based on the total cap of the net instead of transition. Again, DC will try to meet the more restrictive value among the library value and the custom value. So again, the important point to note. So important point to note is max cap makes sense for the output pin of a gate. Max trans is the limit imposed on the input pin of a gate. You can verify this by opening up the library, seeing the .lib file. Please verify this point that where the max cap attribute is defined, where the max trans attribute is defined. Fan out load represents the load presented by the fan out of the cell. The constraint precedence is in this order: minimum cap, max trans, max fan out, max cap. Although DC will try to meet everything, all the design rule constraints before going on to the design goal, but maximum transition has precedence over maximum fan out. If the max fan out is not met, we have to investigate the possibility of a conflicting maximum transition constraint. So if there is a max trans constraint, DC will not make the transition time worse to fix a maximum fan out position. So again, max fan out has a precedence over max cap. What does that mean? So the output pin of a gate might be meeting the max cap, but might be violating the fan out load. So maximum fan out will take precedence in this case, and so idea is that usually the constraints should be such that these design constraints usually go hand in hand. That is, usually they just don't conflict with each other, and they all should be met. But if they are conflicting, if DC is not able to meet one by fixing the other, then these constraints should be revisited. You should check that these constraints are defined correctly, such that DC is able to meet them. Now let's move on to the optimization constraints. So the optimization constraints represent speed and area design goals. Power is the third angle, but we will not discuss it in this lecture. So these are goals. For example, I set a goal of 1 gigahertz on a custom CPU design. Now, what happens if the goal is not met? It might happen that the CPU still runs at 800 megahertz or something. So the constraint, performance constraint, area constraint, both of them should be realistic in nature, such that DC is realistically able to fix those. The timing constraints have higher priority than the area. Will see why. Area is the lowest priority. The priority can be changed, but this is whatever I am talking about. The precedence of priorities. It's all the default case. Anytime by using some commands, you could change the priorities of the constraints. You could tell DC that area is the most important thing for me. So make the area lower, even if the design constraints are violated. DC will do that. By default, it won't do that. You will have to issue some commands. Now the optimization constraints consist of 3 things: input and output delays, which are timing constraints; minimum and maximum delay, which are again timing constraints; and maximum area. So what DC will do once it sees the optimization constraints? What it will do is it will do something, a process which is called timing analysis. What is timing analysis? Timing analysis involves 2 parts. First is delay calculation, that is the calculation of cell delays. The delays are also calculated, but again they are estimated values based on values. Cell delays are calculated using the so for each cell, DC will know what is the load driving, what is the so DC will pick up cells from the library, and then it will optimize the path. So the timing calculation, it will do the timing calculation based on the non-linear delay model in the library, for example, and then it will break the complete design into a set of timing paths. We'll see what are timing paths, and then it will try for each of those timing paths. It will try and see whether the constraint is met. So there are 2 things here, 2 keywords here. One is the timing path, other is the constraint. So let's see. So this type of synthesis is called constraint-driven synthesis. So constraints are defined the limits of the circuit parameters, area, power, and timing. So constraints are the ones used by design compiler for decision making. Should I pick up a 2-input NAND gate or pick up a 3-input NAND gate? The decision is driven by the goals we set using these commands. So timing parameters are, they take priority over design area because the timing constraint, for example, a hold time constraint must be met in all cases. A setup time constraint might not be met, but still the design will perform at lower frequency. But hold constraint should be met to ensure proper operation. We look at synchronous circuits. It means that correct data must be present at the data input of each flip flop or latch before the clock has arrived under all possible conditions. So let's look at timing paths. So for proper constraining, design the tools with PC or even prime time or any synthesis or any timing analysis tool will divide the paths into following. So it will start at the input and it will go through combination logic. Why it will go through combination logic? Combination logic do not have any timing constraint. Is the output of a combinational cell depends on only the present value of the input of the cell. So whatever is the inputs, logic cell will implement the function and it will show some value at the output. But for a sequential cell, the output not only depends on the present input, what was the last input, what is the result, and that is why a flip flop has a setup and a hold timing constraint. This is the only reason why the tools like DC and PT will start from input and stop at any sequential element they see. It starts from input, it goes through combination logic, it stops at the D pin of the first sequential element. So this type of paths are called input register paths. Again, since it stopped here at D, because the setup hold needs to be checked at D. We saw in the library example that the setup and hold timing constraints are defined at the data pin with respect to the clock pin. So again, since the path is broken here, it will start again at the Q pin of the flop, Q pin of the flop, and again traverse through all the combination logic till it hits the next sequential element, D pin. So the second type of path is register to register path. Again, it does that repeatedly till it finds the output. The third type of path is register to output path. So the dashed arrows in these examples, they tell us that these represent the timing path. There could be one more timing path here. It starts from input, goes through combination logic, doesn't find any flop, and goes to an output. It is very common. So this type of path is called completely combination path. That is, the start point here will be the input pin of a design. The end point would be the output port. I should say port. So input port to output port. Now, each timing path has a start point and an end point. Start point is the place where data is launched by the clock. We are talking about synchronous design, so we'll talk in terms of clock edges. So start point is the place where the tool will launch the data. So what this start point could be, I discussed this. It could be the input port or the Q pin of a sequential element. Oh, sorry, the clock pin of the sequential element, because the trigger is the clock. So it could be either the sequential element's clock pin or an input port. Data is propagated through combination path and then captured at another clock edge. So now we are talking about setup. We are talking about the max timing constraint. Let's not worry about hold. Synthesis doesn't do much about hold, because hold time, first of all, if we go back to the equations, I deal with these equations in much more detail in unit 5, but we have seen these equations earlier, the setup and hold equations. If we go back to these equations, we see that the hold timing equation does not have the clock frequency dependency. What it means is that to meet hold timing, since the whole time equation does not have a clock frequency in its equation, if the whole timing fails, there is nothing we could do. The chip fails, the design fails. But the whole timing constraints, the whole timing paths, they depend a lot on the clock tree after the physical design is done. Since design compiler does not have any information about the clock tree, it does not fix hole unless and until we tell it explicitly to do it. The design compiler, the aim of synthesis is to fix performance issues, is to convert RTL into gates such that it meets the performance, that is the clock frequency criteria. This criteria is represented by the setup time equation. So setup time is a factor in this equation. This is why the timing tool, that is either design compiler or PP, will launch the data on one edge and expect the data to arrive at another edge, at the second edge, but still meeting the setup time window of the capture clock. So each timing path has a start point, which can either be an input port or the clock pin of the sequential element. The data will be launched. The next edge, the data will be captured at either sequential element's data input pin or the output port. So when we define the clock, so let's go back to the figure of the timing path. Let's focus on the register to register path. Now, what does DC know? We haven't specified anything yet. We have just read in our RTN. We have just said the design environment. We haven't said any design constraints till now. So what does DC know? DC knows the delay of this clock from the library. It knows the delay. So DC is already optimized. That is, DC is already DC will know the delay of this combination logic. So DC knows all the cell delays, whatever is there in your design. Obviously, the cells will only come after optimization. But assume that you did not provide anything apart from the design constraints, libraries, and RTL. We did not define any optimization constraint and went through the synthesis. DC will still do the synthesis. It will still do synthesis even if it does not know what your goals are. It will by default optimize for lowest area. So the design will be the resultant design will be very slow, but it will be area efficient. But since there are no goals in place, it's irrelevant. But what I'm trying to say is that DC knows the cell delays from the library. It will know the net delays, that is the estimated values from the variable model. The only thing missing here, what DC does not know, is the clock frequency. So as soon as we tell DC that okay, the clock which is driving at CLK is of, let's say, 200 megahertz. If we tell DC this, all register to register paths are constrained. So the equation here is that the clock to Q delay. So there are three things here: the clock to Q delay, combination logic delay. The sum of these two, the data will be launched at this clock edge. It will arrive at D after the delay of a flop plus the combination logic, and it should arrive here before the setup time of the next clock edge. Difference between the two consecutive clock edges represent the time period of the clock, the inverse of which is the frequency. So just by defining the frequency of CLK, we constrained all register to register paths. So clock will set constraint on all register to register paths. Things become a bit different for boundary. That is, at the input port, we don't know mostly what kind of data is coming and at what time the data is coming. So we have a concept of input delay. Similarly, at the output port, we do not know what is the capture logic. So we have a concept of the output delay. These two things, input delay and output delay, in many cases these are estimated values. We'll see how to estimate these values. So for the boundary, additional data is required. So one thing required is clock. For the input parts, the arrival time of the data is unknown. For output port, the external logic delay is unknown. In order to analyze the input register and register to output timing, external timing conditions must be specified. Input delay is defined as the external delay before input. Output delay is defined as the delay of the circuitry between output and the next register. Please note, both input and output delay are for the external world. They are not for your design, because you know input delay and output delay will be estimated values for the external interface. And let's see how these values are used to constrain these paths. So input delay is now this is the design boundary. This is the design boundary. Clock coming is in a CLK. Input port is in. This part which is left of input port, we don't know much about this. We can assume that this is coming from the same clock. It is a valid assumption in most of the cases. It is coming from the same clock domain, and it takes some amount of time. It is mostly driven by a clock. It takes some amount of time to reach the input. This amount of time, this estimated amount of time, is called the input delay. Output delay, again, this is the boundary. This is the design boundary, output port. Again, this is the part we don't know about. So we tell DC that we tell a DC by using the set output delay command. We tell the estimate. We estimate that the external world will take X amount of time. This is called the output delay. Timing budgeting is the term which is used to estimate the value of the input delay and the output delays. We have to make sure that there is enough margin in our design such that external circuitry can be connected to it properly. The timing does not violate. So how do we do timing? How do we budget? Right? That's the question. How do we calculate the values of input and output delays? Usually, in most of the blocks, people will set some guidelines. For example, some designer might set a guideline that the input and output delay are both 40% of the clock period. 40% of the clock period means that, for example, you have a 10ns, you have a 100 megahertz clock, and you say that the input delay is 40%, that is 4ns. So input delay and output delay are always with respect to some clock. So if we say that the input delay is 40%, it means that the 40% of the clock period of the capture clock is reserved for the external world. What does that mean is that the external world will consume the amount equal to the input delay from your clock period. So in this case, the input port at which we applied the input delay of 4ns of 40%, we consume 4ns, and remaining 6ns is left for your design to consume. So you should make sure that the logic from input port to the first sequential element does not consume more than 6 nanoseconds. So this is the idea. So now design compiler knows that the constraint from input port to the first sequential element is that it should not consume more than 6 nanoseconds. This is how the input to register paths are constrained. I'll have a lot of these type of equations in unit 5 that will make things much more clear, because static timing analysis is much more extensive than the optimization constraints used by design compiler. So since design compiler is only focused on performance, so it needs to know what is the goal. Again, if we say that the output delay is equal to 40% for a 10 ns period, 10 nanosecond period, it will amount to 4 ns. Again, the remaining 6 nanoseconds is for your block. You can use it inside your block. So now let's say we set these to be 40%, and then after connection to each other, if this kept in all, then after connection to there will be a 20% period margin. So what if the slide recommends is that you set a particular value on input delay and output delay, for example 40%, and then try to keep some margin for this margin will take into account all the post layout variations, considerations, the net length, the net loading and all. So it's saying that the remaining out of remaining 60%, you could take again 20% as a margin. So it's just a different way of saying it. You could say that you could increase the output delay or input delay in many designs. So now see, so there are a couple of recommendations of RTL design. Is that include register or input or register or output? Why is that? So now we do not know what kind of, if we do not know what kind of logic is going to drive the input port of the design. So for example, this is my design, and I do not know what kind of how heavy this logic is, this external world logic is. Right? If we do not know how heavy this is, and if we consume more delay between this port and the clock here, then it is going to be detrimental to connect the external heavy design. So we could simply register the input port. That means the combination logic here is almost negligible. So we consume very less delay from input port to the sequential element. This will allow us to give majority of the time available to us, that is most of the clock period available to us, to external world. I have seen designers who give up to 80% of the clock period as input and output delay. This is only possible when you register both inputs and outputs. So now we saw how the register to register paths are constrained by defining clock. We saw how input to register and register to output paths are constrained by defining input delay and output delay. Let me just go back and review the commands. So again, we'll have dedicated lab sessions, lab videos. Meanwhile, I would like you to go through the man page and the help of these commands. So I would like you to focus on these three commands: set max function, set max timeout, and set max capacitance. Although I would not recommend to use these in the initial trials of a design. These can be used later, but it's good to know them. It's good to know what they do. So it will be useful to study the man page and the help of these commands. So we saw that for timing constraints, to actually constrain the register to register path, the only thing you need to define is the clock. So the command is called create clock. I'll go over this create clock in the lab session in detail. Then to constrain the input to register path, there's a command called set input delay. To constrain the register to output path, there's a command called set output delay. So these three commands, create clock, input delay, and set output delay, in total they constrained all the three kinds of timing paths. Now I also told that there's one more type of path, which is the combination path, the complete combination path, which will go directly from input to output. So now how do we constrain it? So one constraint we could say is that set max delay or set min delay. Please don't worry about set min delay for now. The command you could use is set max delay. You could tell DC that the full combinational cloud between input port and the output port of my design should not take more than, let's say, 5 nanoseconds. So you could say set max delay 5 ns from input to output port. This will let DC know that I need to optimize this logic to meet this goal. There is one other technique which is called the technique of virtual clock. So I'll just discuss this technique for now. You could choose to study more about it and use it in your synthesis, or you could choose to use the set match tool. Doesn't make much of a difference for synthesis. However, virtual clocks are very much useful for timing analysis. When we go to unit 5, we'll know why. So I'll just list down the method. So in some cases, it is necessary to create a clock that is not part of the design, but it's part of the system. That is, it is. Let's say now here. Let's go back to the. So now let's take this case. So now the design, my design, is the design I am planning to synthesize. Now let's say the clock here. So this is the clock port. Let's say the external world. In the external world, there is some other clock that drives this input. It's not the same clock, but this clock, this external clock, whatever the clock used externally, is nowhere used in your design. The only use it has is that it launches the input data. So now this is the case where this external clock is not part of our design, but it's part of the system in which our design will sit. This is what is said here. It is sometimes it is necessary to create a clock that exists in the system but not in the design. Now, the create clock command needs the pin on which the clock should be defined. For example, the clock port of a design is called CLK. You say create clock minus period 10 nanoseconds, and you tell what port to create the clock on, which is CLK. But now, if the clock is not actually part of a design, there will not be any port associated with it. So if you give this command without the port, design compiler will create a clock and call it a virtual clock. Virtual means it does not have any real source. So when a source object is not specified, a virtual clock is used, which does not physically exist in the design. So the source object represents the place of the clock in the design. A source object can be input port or a pin inside the design. So whenever you create a clock, in most of the cases you need to specify whether you are creating a clock at the input port or a pin inside the design. If this source is missing, then the clock is called a virtual clock. Virtual clock obviously has no sources. It exists in the memory, but it is not part of the design. You can, however, define input delays and output delays with respect to this virtual clock. Now, set input delay and set output delay commands should always be used with some clock. They should not be used. They can be used. This will not be there, but it does not make sense. They should always be used in conjunction with some clock. Now, this clock could be a real clock or a virtual clock, as the case may be. Since it's not physically present in the design, it is not connected to any port of the design. This is one example. The constraint using virtual clock. So assume that CLK here is a virtual clock because it does not. So my design is wholly combinational in nature. It doesn't get any clock pin, but I know that some kind of sequential logic will drive the input and capture the output. So I assume that there is a virtual clock called CLK. Now let's say the CLK is the period is 10 nanoseconds. Let's say the period is 10, and I say that the input delay here is, let's say, 2ns, and output delay here is 2ns with respect to this clock, with respect to CLK. Now CLK is a virtual clock again. So what DC would do? It will start at the timing path. The timing path starts at the input port. The timing path will start here. DC, since the input delay is 2, DC knows that it will say that the clock is arrived at 0. It will always start with 0. The clock is arrived at 0. and since the input delay is 2, DC will assume the arrival at 2 ns. Clock is at 0, input comes at 2. Whatever delay this combination logic takes, for example, let it be anything, let's say it takes x. So data arrives here at 2 plus x. Again, output delay of 2 ns means that the output world here with the external world here will consume 2. So the total delay is 2 plus 2 plus x. Now since 2 plus 2 plus x should meet 10 ns, the x should meet 10 minus 2 for input delay, 2 for output delay. So this combination logic delay is now constrained to take a maximum delay of 6 nanoseconds. So if this is how, by using virtual clocks, you can constrain the combination paths. It's very simple. The constraint, what is the constraint? The constraint is that the maximum time is clock period minus input delay minus output delay. This is the constraint. Now let's see a bit about clock. So what attributes does the clock have? So there will be, the clock has a period which represents the period is the time between two clock edges, two consecutive clock edges, which is nothing but the invert of which is the frequency. A clock will have some amount of transition time. It will take a realistic clock, ideal clock will have a 0 transition time from 0 to 1, but a real clock will have some transition time. It will take a finite amount of time to rise from 0 to VDD, so it has some transition time. It has a waveform. Not all clocks have a 50-50 duty cycle, 50% duty cycle. A clock might have a 10% duty cycle or 20% duty cycle. This is represented by the waveform. Then latency, that is how much time does the clock take from the place where it's actually physically present to reach to your design. This is called latency. Then there's something called uncertainty, which tells us that models the clock jitter. Most of the clocks will come from PLL. The PLL clock has some jitter in it. That is, even if let's say you say that the PLL gives a 10 nanosecond clock, the two edges will have some jitter, so the period will be very close to 10 in most of the cases, but not exactly 10. So uncertainty actually will represent that effect, that physical effect. So at synthesis level, the tool will assume ideal clock. What it means that it will not have any uncertainty by default, no latency, no transition, because it doesn't know anything. This is why these parameters must be modeled at synthesis step. What it knows and what it should know is the period, because that defines the performance parameter, and the waveform. These two are important things. These two are default. They will come as part of the create clock command, but other things have to be told using separate commands. So there is a command called set clock latency, which models the clock latency. Latency is the time it takes from clock to be propagated from clock source to the sequential element in the design. It has two components: source latency and network latency. So let's say this is the design boundary, and we know that at the chip the clock will come out of a PLL. So the time it takes here, this time either can be estimated or accurately determined depending on what stage your chip is in. This time is called the source latency. Network latency is the delay from the clock definition point to the register point. So network latency will be different for each of the clocks, because the time it takes for the clock to propagate from the input port to the clock pins of the clocks will be different for each clock depending on what is the logic in the field in the clock path. This is why it is since DC by default will not know these values, it is essential to provide these values. In many cases, source latency does not matter for timing calculation, but network latency does. Clock uncertainty is the greatest difference between arrival of a clock signal at register in one clock domain or between domains. So what it tells here that clock at A arrives at some point, clock at B arrives after some delay because of this delay element here. So this difference in delay is called the skew. Now this skew will change the way the equations work. This skew, if the capture clock is delayed, what does it mean? If the capture clock is delayed compared to the source clock, the launch clock, the time available is increased since the capture is coming late. It should have come at X, it's coming at X plus T. So more time is available for the operation. It is good for setup, but again on the other hand not good for hold. So clock uncertainty we'll see in unit 5 we'll see a lot more detail into clock uncertainty. In fact not even uncertainty but all the parameters, the latency, the uncertainty, the function and so on. But for synthesis purpose, it's a good practice to apply some value of uncertainty to model the clock tree effect that will come in the post layout, plus in modeling the jitter effect. So thing to remember is that uncertainty will have two parameters in synthesis. One is the clock tree estimation, other is the jitter estimation. So clock tree estimation, so for example in particular technology, designer might say, okay, I'll keep a blanket uncertainty of 200 PS. So you apply that uncertainty for all the clocks in the design, 200 PS standard for all the clocks in the design. So there can be different guidelines depending on how your block is, how big your block is, what technology your chip is in, and so on. So the variation in the generation of clock successive edges with respect to nominal times represent the simple uncertainty. The variation, so this in fact the figure on the left hand side, it represents the clock tree. So this type of structure where you have buffer trees, it represents the variation in the clock. So clock is supposed to reach at both these points at the same time, the clock edges, but it does not happen obviously. There is some difference. This difference is due to the clock tree variation after the clock tree gets built, or there could be the launch and capture clock are working on different clocks. So this is the uncertainty which is coming as a result of the design itself. There can be two factors to it. The third factor is the transition time. The time during which the signal changes from logic low to logic high or from logic high to logic low. The delay at the output and the transition time of the output signals. So if you don't specify anything, the clock transition time would be 0. But this is not realistic. You should apply some value. Let's say you could apply 100 PS transition on the clock. What does this affect? This affects the setup and a hold constraint time calculation. If you go back to only the delay model, you would see that setup time of D depends on the transition at D plus transition at clock. The clock transition will change the way DC calculates the value of the setup and hold limit. So this was all about clocks. We will see a lot more detail in Unit 5 about clocks. That's why I am not discussing all the equations here. Unit 5 is a lot of equations, but for synthesis purpose, as far as design constraints are concerned, you should worry about the three commands majorly. So design, I'll not summarize DRC anymore. DRC is clear; it mostly comes from the library itself. So for optimization constraints, for area, in most of the cases you could set max area to be 0. This tells DC that there is no limit to which you can reduce the area, so DC will work hardest. Although it is not very realistic, but many people they just say set max area 0 in all the cases, which is a good practice, I would say, for smaller designs. For speed, create clock, set input delay, set output delay. These are the three most important commands that you should remember. As far as setting the clock parameters is concerned, they are more useful for timing analysis than compared to synthesis. So once you define the clocks, define the input delay, define the output delay, all the timing paths are constrained. For completely combinational paths, you could use virtual clock or you could use set max delay command. Don't worry much about set min delay, we will use afterwards. So these 4 commands will constrain all the timing paths, and you could start with the process of issuing the compile command. We will see how the compile command is used, what are the different synthesis strategies which you could use to synthesize your design in the next lecture. Thank you.